And the morning session was pretty much devoted to issues having to do with quantum computing. The afternoon sessions are going to be more about quantum information. And so our first talk is going to be by Eric Chitambar at the University of Illinois. And he is going to be telling us about quantum resource theories. That's been a very active subject in about the last 5 years. And so I'm looking forward to hearing the talk. So, okay, go ahead, Eric.
Great. Thank you, Mark. And I appreciate the opportunity to come and talk to you guys today about quantum resource theories. It would, of course, have been nice to deliver this talk in person and get to know you guys personally, but, well, here we are. I would like this to be somewhat informal in the sense that if you have questions, please stop me right away. I'm working on a tablet here, so if at any point we need to write something down or I can explain something in greater detail, just stop me, and that's no problem. And so I have a second screen up so I can see if you're raising a hand, but also just yell out or put it in the chat or something. I should be able to see that. All right, so this talk is going to be an introduction to quantum resource theories. And if you've never heard of a quantum resource theory, or maybe you have, but you're not entirely sure of what it is or why it's interesting, hopefully by the end of the talk, you will have a sense for what a quantum resource theory is. So here's the 5 steps to this presentation. First, I want to start and provide somewhat of a philosophical or a broad motivation for quantum resource theories, and I'm going to appeal to some results in thermodynamics and statistical decision problems. And then we'll extend that into quantum information processing. Then I'll define for you the structure of a quantum resource theory, and particularly we'll look at some of its features. We'll see an example, the quintessential example of a quantum resource theory is the theory of entanglement. Then we'll discuss the difference between a static and a dynamic quantum resource theory. And as an example of a dynamic resource theory, we'll look at the resource theory of measurement compatibility. And finally, or rather the resource theory of measurement incompatibility. So it should be incompatibility, that's the resource there. And then there's just one slide to close up and to point out some potential future directions. Okay, so let's get to it. I want to put your thermodynamics hat on and consider the following scenario where it's a very sort of simple experiment where we have a cylinder with a piston on it, and inside the cylinder there's a fixed number of particles, and let's say it's of the same species. So everything is simplified here. And there are 2 parameters characterizing the system. There's its energy, U, and the volume of the cylinder, V. Okay? So we can describe the state of this piston by U and V, 2 parameters. Well, okay, great. And we can also consider transformations, state transformations, where we move the piston up and down. And what will happen is that we'll go from one parameter, one set, V1, U1, to another set, V1, V2, U2. And that will just define for us a state transformation. Okay, so the question you can ask then is, what sort of state transformations are possible? So pictorially, we can represent this by, here we have our UV plane, and we could say, let's say we have a state transformation if we can go from one point to another, and let's ask what transformations are possible. Well, of course, the answer is that you can do any transformation if you're allowed to add arbitrary amounts of energy or heat and do arbitrary work on your system. But what we're interested in here is to place certain restrictions on the allowable processes. And when we place restrictions on the processes, then there will be limitations to what state transformations are possible. Okay, so specifically, I want to look at a class of operations which are called adiabatic processes. You may have seen these before in your thermodynamics studies, most likely you have, but if you haven't, I'm going to describe it for you. So what does this consist of? And I want am I allowed to do? I'm restricted to only doing adiabatic processes. What does that entail for me? So we'll call these the free or the allowable operations. Okay, so here's what you can do. You can introduce some external device. And this could be, it could be a motor, a heating plate, anything, any other device you want to use. And its initial state will be gamma naught. Then you can introduce some interaction between your piston and the device, but you also need to hook this device up to a weight. And what this weight is going to do, it's going to characterize the amount of work that's being done on the piston. So specifically, as this device does its processes, whatever it's doing, it's going to cause a state transformation on your piston. But it's also going to cause the weight to either go up or down. And what we demand is that in this state transformation, the device returns to its original state, gamma naught. Okay, so if you can go from U1 V1 to U2 V2 by such a process, then that is an adiabatic process. Okay, and the intuition here is that any change of the system can be accounted for by mechanical energy of this weight that's going up or down. All right, so the question, what state transformations are possible by such a process? And we can use some symbols here to write this. Let's say that X is majorized by Y if X to Y is an achievable transformation by some adiabatic process. And here X is one tuple, V1, U1, and Y is another, V2, U2. All right, and you may have guessed what the result here is, but it's nothing more than the second law of thermodynamics. And what it says is that you can perform a state transformation. You can go from one state to another if and only if your entropy is non-decreasing. Right? So S here is the entropy of the state. Okay, so one thing that's nice about this result is that it allows us to form what's known as a total order on the system of all states, meaning that because if I have an X and a Y, it will always be the case that either X will be less than or equal to Y or it won't be. So there will be an answer to this question. It's an if and only if. So that then imposes for us a total order on the set of states for our system. Okay, any questions on this so far? This is kind of some stuff you'd see in intro thermodynamics course. All right, let's shift gears. And I want to discuss something known as a statistical decision problem. And so here's the scenario where you have some random variable, some object that is a stochastic process. And you can think about this as, this is a category die. But think of it as a source that's going to produce some outcome X. All right, so this would be the face of the die after you roll it. Then this outcome X is subject to some noisy channel. All right, so the noisy channel, what it'll do is it'll flip the value X to Y with some probability. And that transition is just described by the conditional probabilities of the channel. All right, then you, as the experimenter here, you look at this value Y, and what you do is you make a guess. And your guess is going to be Z. So Z is a function of Y, and this is like your decision. So all you're observing is Y, and you make a guess Z. And well, what do you determine what your guess Z should be? Well, it's going to be guided by some payoff function. Okay, so the payoff function is a function of the actual output X and your guess Z. And that's going to give you some money, some payoff. So if your source is uniform, and for simplicity, let's just assume that it's a finite outcome source, then the average payoff is just given by 1 over the number of outcomes, and then the probability of you guessing Z and the output being X. Right, so you can kind of read this. So this was X was converted into Y, and then dy was your guess. So this is your Z here. And then that's the payoff you get. All right. So here in practice, what will happen is the experimenter will want to choose a decision function that maximizes the average payoff. Right. So the experimenter here knows the source, knows the channel, knows the payoff. And so then he or she needs to decide what should be my function if I want to maximize this average payoff. Okay, so let's write this down for as payoff max or dollar max. And so here, what we're doing is we're maximizing over all the decision functions. All right, good. So this function here that I defined for us, it's very useful because for a fixed payoff function, it provides for us one figure of merit for the channel n. Right? So specifically, I can say, if I have a payoff function, how good is this channel at allowing me to maximize my payoff? So this is some characteristic or some figure of merit for the channel n. All right. So now let's ask this question. So suppose we transform our channel. So this is some noisy channel we have, but we want to convert it into another channel, M. And this is the analog to a thermodynamic transformation, state transformation that we saw in the previous slides. Okay, so I'm going from an N to an M. The question is, how does this function, which I just told you is some quantifier of the channel, how does its value, payoff max, compare as you do this transformation? Well, of course, it will depend on the type of channel transformation you perform. So let's think again, as we're the experimenter, and there's certain restrictions imposed on what we can do. So what are the allowed transformations? What are the free operations that we can do? So we're starting off with this channel N, and we're going to convert it to another channel M. And let's look at one specific type of transformations, which involves applying some additional post-processing channel. So what that means is that we just wire a new channel K for output Y, then it gives an additional process. And then what you end up getting is some new channel M, right? It accepts X and it outputs Y prime. But if you opened up this box and you asked what's going on, you just started with your original channel N, then you tacked on this final post-processing channel. Okay, so for two channels, N and M, we can say that N is majorized by N if there exists such a transformation, right? I can go from N to M by post-processing. And intuitively, you can think about this as saying N is more informative than M. Why is that the case? Well, you can think about when you tack on post-processing, it introduces more noise, right? So imagine in the extreme case that N is a noiseless channel. It's just perfectly sending input to output. So that would be very useful in communication settings. It would allow you to transmit a lot of information. But now you tack on this post-processing, it's going to add some noise. So it's going to spoil that perfect information transfer. Okay, so let's plug it into this decision problem. So now here was our original channel N, and now we've sandwiched in a post-processing. So what the experimenter sees is Y prime. Sees the output of that post-process. And the result here is the famous BSS theorem, which says that you can do this conversion from N to M if and only if the payoff function is no less for N than it is for M for all choices of payoff functions. Okay, so what we've done here is this majorization. This is a very operational idea. It's converting one channel to another. And we've shown that it's equivalent to, on the right-hand side, this is some family of quantifiers, some measures of our channels, right? How well it can perform for a particular payoff function. And so this theorem then relates the operation to the quantifier of the channels. All right, one comment here is that if we compare this to the previous entropy result, here we don't have a total order on the set of channels, we have what's a partial order. And the reason is because you have to check all payoff functions omega, right? So it's not just one relationship, it's not just the entropy of one is larger than the other, but there's actually a whole family of measures that you need to check. Okay, I'm going to give you a third example here, and hopefully the point will be obvious to you at the end of it. So now this is a quantum one. So consider two quantum systems. controlled by Alice and Bob. So Alice has one part, Bob has the other. If you think of it, your favorite quantum system, maybe 2 photons is good, an entangled pair of photons. And their joint state is in some pure state psi. Again, it's arbitrary, but in general, this could be some entangled state. And the question is, they want to know whether they can convert their state psi to another state phi. Okay, so again, in principle, this you can always do a state transformation going from psi to phi if any physical interaction is allowed between the systems. But that's really not what's interesting. What's interesting is whether this transformation is possible under certain limitations of the allowed operations. And in particular, we want to pinpoint operations that are physically motivated. Okay, so what are the free things that make sense to consider in this problem? And well, let's think about it. So we have 2 parties, Alice and Bob, and we envision them being somewhat spatially separated. If we're going to make this distinction between 2 different experimenters, then it makes sense for them to be spatially apart from one another. If they're right next to each other, then it's effectively one experimenter. Right? So we have in mind this sort of distant lab setting where you have 2 laboratories that are spatially separated. And connecting them is only a classical communication channel. So they're not allowed to send quantum signals back and forth. And intuitively, this reflects sort of where we are experimentally. We're not able to do long distance quantum communication. Classical communication is free for us, it's cheap. So we want to consider information processing in this particular paradigm. And what happens is that Alice in her laboratory does some quantum operation. Okay, and the M1 here, these are outcomes of her operation. In a quantum measurement or quantum operation, you have some classical output. This could represent your measurement outcome. And she's allowed to send that over to Bob, over the classical channel that they share. Then on Bob's end, he's going to choose some operation to perform in his lab, and it's going to be conditioned on the classical information that Alice sent him. All right, and this goes back and forth, so it has this kind of ping pong structure. And you can build up then actually a very complicated set of quantum operations by this back and forth classical communication. And any process that can be done in this way is known as LOCC, or local quantum operations in classical communication. All right, and these are the restrictions that we want to look at. So I've given physical motivation, and now let's impose this physical motivation onto the mathematical problem. So for any two states, psi and phi, let's say that psi is majorized by phi if it's possible to convert psi to phi by this LOCC process. And the result was a very celebrated result in the field, was shown by Michael Nielsen, is that this transformation is possible if and only if you have this series of set of inequalities satisfied, where these EKs are defined as follow. They're known as chi-fan norms. And basically, they're just functions of the Schmidt coefficients. So for those who have worked with entangled states before, you know every entangled state has a Schmidt decomposition. And I can consider then the Schmidt coefficients, and I can, for every entangled state, I can look at its Schmidt coefficients, and I can make a vector of them. If I square them, I'm going to get a probability distribution. So that defines me a probability distribution. And then I can define these norms on the probability distribution, known as the chi-fan norms. Okay. And so here, there's actually a finite set of inequalities here. Whereas if you go back to the situation of the statistical decision problem, it was over all payoff functions. And in fact, that's an infinite family of functions. Here, there's only a finite number that's bounded by the dimension. Okay, and again, here because there's more than one function, we have a partial order. All right, here's the summary slide of what we've discussed so far. So I've given you 3 seemingly very different problems in different subjects, but they have this similar structure in terms of converting one object to another under restricted operations. And it's determined by some set of functions. So lesson 1 for this workshop, or at least my lecture of the workshop, is that placing constraints on physical processes leads to a partial ordering of objects. It could be a total ordering in the case of adiabatic, okay, but in general, it's some partial ordering. And second is that these constraints leads to certain quantities that cannot be increased, right? And what I mean by cannot be increased is under these constrained operations, you're not able to decrease the entropy, right? Or you're not able to increase the average payoff, or you're not able to increase the chi-fan norm. So these are then quantities or measures of some property of your state that you're not able to increase under the restricted operations. And this is exactly the heart of a resource theory, is this type of structure. Yeah, so what we'll identify these quantities as being a resource quantifier. Okay, those are specific examples. Let me kind of sketch out the general framework of a quantum resource theory. But before I do that, I want to make just one slide or a brief discussion on the meaning of quantum operations. So for those who have seen this before, this is kind of a review on things, but it's for those who have not, it might be helpful to clarify what I mean by quantum operations. So a quantum operation, it describes the most general evolution that an experimenter can perform on a quantum system. So we imagine we have some system Q, and we can ask, what are we allowed to do with it? What does nature allow? Okay, so according to quantum mechanics, the most general process is the following, is that we can introduce some ancilla system R, or some additional system. And then what we do is we introduce an interaction Hamiltonian between the two for some fixed time period. And that will then generate for us a unitary transformation. And what pops out on the other end is an S prime R prime system. And we can measure this R prime system. Okay. So if we abstract this, if we kind of just look at the end of the day, what we've done is we've actually generated some map where we input a quantum system and we get out a quantum system, but we also get out a classical system, right? This classical system, let's go back to where this came from. The classical system was for measuring part of this subsystem. And so if you look at the structure of this a little closely, you'll see that this mapping is what's known as a completely positive trace preserving map. Okay, which we don't have time to get into now. We can talk about it later, but just understand this is a type of a mathematical transformation from the set of density matrices to the set of density matrices. Okay, so DS is the set of density matrices on S, and S prime D, S prime X prime are the S prime X are the set of density matrices on the output quantum system and classical system. So this is what's also known as a quantum channel. Okay, good. So now that we have that in mind, we can write down a definition for what a quantum resource theory is. So it's actually just a prescription of sets of quantum states and sets of CP-TP maps. So let S and S bar be arbitrary systems. And then a quantum resource theory identifies for us a set of density operators, this is a subset of all the density operators on S, and this is a subset of all the density operators on S bar, and then a collection of maps from S to S bar. Right? And it has to satisfy this crucial property that if I take any channel in my set of operations and I apply it to an element of S of Fs, then I have to get an element in Fs bar. Okay. So the picture is this. So here's DS. These are all my set of density matrices, and then I have a subset Fs, and then I apply my channel. And if I start off with a density matrix in this Fs subset, I have to convert it over here into the target subset. And so these are called, the subset is known as free states. Okay, so I have my total set of states, and then I identify a set of free states. And then these maps that have this property are known as the free operations. Okay, these are what I'm allowed to do in my resource theory. And then the idea is that any density matrix that lies outside of the free states is said to possess some sort of resource. So we call it a resource state. And why does it have a resource? Well, think about it. If I start off with a free state, I can never map it to anything outside of the free states. I can't map it to a resource state. Right? By this closure property, if I start with a free state, I have to end with a free state. I'm not able to generate resource using my allowed operations. Okay, good. So that's the basic framework of a resource theory. Let's look at this as the prime example is quantum entanglement. We've already seen it when we talked about the resource theory, or we talked about the entanglement transformation problem. But let's look at it in a bit more detail. So here, the free operations are LOCC, which we just discussed in the previous slide. And then the free states are those that the free states are those that can be generated by LOCC. Okay, let's look at what those states look like. So imagine in our distant lab, we have Alice has prepared some density matrix rho A and Bob has prepared another density matrix rho B. And then they engaged in this ping pong protocol going back and forth. So they're allowed to exchange classical information. And what you end up getting is something that looks like this, if you were to write it out. All right? And in a bit cleaner form here, the state that you generate has this convex combination of product states structure. And these are what are known as separable states. Okay. So using this idea of a resource framework, we can now answer this question: what is entanglement? Right? So I mean, this is, if someone just walked up to you on the street and asked you, what is quantum entanglement? Right? I mean, you would maybe scratch your head a little bit and try to think, well, what is this person asking me? Are we want some sort of philosophical discussion here, or do we want a rigorous mathematical definition? Here's a definition that I think is very nice, and it's an operational definition. And you say a quantum state is entangled if and only if it cannot be generated by LOCC. Okay, meaning that it doesn't have this separable form that we just saw on the previous slide. And what's nice about this is that it actually places the operations on a more fundamental level, right? It's the LOCC that's fundamental. And then what comes out of that, an implication, is that you have entanglement. These are states that you can't generate by LOCC. And so it really places the emphasis on the allowed operations. Okay, so that was an example of one resource theory. Let me just list you some reasons of why you might be interested in studying this. So there's practical motivations. Typically in an experiment, there are some natural restrictions that are in play. Maybe you can't afford the most expensive experimental device, or there's some problem in the lab that you can't overcome and you just have to deal with it for some constraint. And so that describes the situation of a resource theory. There's some limitations on what you can do. So understanding those limitations are, of course, very important for experimental implementations and quantum information processing in those environments. It allows you to quantify the resourcefulness of different quantum states and processes. Right, and as we've seen, it allows you to come up with methods for transforming resources from one form to another. So those are very practical reasons. More fundamentally, as we've seen, that it allows you to come up with operational definitions for primitive features of quantum mechanics like entanglement, and you can do something similar for non-locality or quantum coherence. These are concepts that we have, but now we can root them in terms of physical processes. And a huge benefit of this resource theory framework is it allows for a unification of seemingly different objects in quantum and classical information theory. And we've already seen that, right? When we looked at the thermodynamics and we looked at statistical decision problems and we looked at entanglement transformation, we saw that all three of these had a similar structure. And so what that means is that if you develop a set of tools, mathematical tools to study one problem, then you can apply it to the other because we've now appealed to this abstract level where there are common features. So it gives you a new way to attack problems that perhaps you hadn't recognized if you just studied the problem in itself without understanding the broader framework it can be placed in. Okay, here's some examples of quantum resource theories. We talked a bit about the entanglement. I mean, this is certainly a non-exhaustive list. And as Mark pointed out, in the last 5 to 10 years, there's been quite a bit of work on quantum resource theories. But they all have the same features. They identify some set of free states and then some free operations. Okay, so let me talk a bit more about the quantifying and detecting of general resources. So now that we say you've come down and you've identified your free operations and you identified your free states, and now you actually want to come up with a way of quantifying the amount of resource in a given state. Okay, so in general, there won't be one single way to measure resource. In the same way that there's not one single way to quantify distance in a metric space, right? The way you learn about metrics is that it's any function that satisfies a certain set of properties. And likewise, you have the same idea for resource measures. And one of the axioms that a resource measure must satisfy, if not the only one, is what's known as the golden rule of resource. And that it's the function, the resource quantifier must be monotonically decreasing under the free operations. So you come up with this phi here, and this is mapping density matrices to real numbers, and you can't increase it under all your free maps E. Okay. So we've seen examples of this in adiabatic transformations. It's minus the entropy. For the channel post-processing resource theory, it's this max payoff function. And for LOCC, it's the Kaifan norms. These are examples of these resource quantifiers. And they satisfy this golden rule. Okay. So another family of resource quantifiers is based on distance in the space of Hermitian operators that contains the density matrices. So this is a kind of a mathematical idea. And here, pictorially, what you have is, you imagine you have your set of density matrices, and you've made this division between free states and resource states, and now you're given some resource state rho. And what you can do is you can ask, what is the closest free state to my density matrix rho? So geometrically, you imagine this is some line that's going from rho to your set of free states. And then you find what that minimum distance is. And so you can define this as RD. And this is going to give you some quantifier of resource, right? How far away you are from the set of free states. This will depend on your choice of distance measure, right? On the space of Hermitian operators. And so here are some examples. So you could define the trace norm, which is just, you take the difference between rho and omega. So at this point here, that would be your omega. That may be your closest free state. And you just look at the distance as measured by the trace norm. Another measure, which actually isn't a proper distance measure, but it works in terms of quantifying closeness, and it can be used to bound true distance measures, is the relative entropy of resource. So here D is your relative entropy between two density matrices, rho and omega, and you just minimize that quantity. Okay, sticking with this geometric picture, provided that this set of free states is convex, convex meaning that if I take any 2 points and I draw a line connecting those 2 points, I stay within that set. Provided that's a convex set, then I can use a famous result, which says that there's, for any state outside of that convex set, there exists a hyperplane, which separates our state from this convex set. All right? And mathematically, what this hyperplane is it's just a Hermitian operator or a quantum observable. And if we form the expectation with respect to that observable, so if I look at this Hilbert-Schmidt inner product, meaning I take trace W rho, this observable has the property that it will be negative for this particular state rho. But if I were to take the same inner product with any free states, I get a positive value. Okay, so this is known as a witness for my resource. Right? And the idea is that suppose you are in the laboratory and you prepare a state rho, and you claim, you say, hey, I've just created this very resourceful state rho. Well, someone could say, well, how do I know, right? You just have, all I'm looking at here in the laboratory is just some tabletop experiment or setup of various devices. Like, how do I know that this actually has that resource? Well, you could invoke the theory of witnesses, and you could say, well, I'm able to perform this measurement W, and I know that if this were a free state, then I would have to have some expected value of W that's non-zero. So you're running this many, many times, right? So you're getting some sample average that's turning out to be positive. However, when I measure my state rho here, I actually get something that's negative. So mathematically, if I assume that this is accurately characterizing the system that I've created, then therefore I will have detected the resource. Okay. All right. Any questions on this so far? I know we're covering a lot of ground here. Okay. I want to make a distinction now between static and dynamic resources. Okay, so now we're going to generalize. We're going to another level. Static resources would be states, quantum states. It's something you can think about as like a snapshot in time, describing the state of my system at one element in time. A dynamic resource would be something that causes a state transformation. So we're talking about something that lasts over a finite duration of time. And we've seen both examples so far. So when we talked about the statistical decision problem, we were looking at channels, right? So that was a dynamic object. When we were talking about our thermodynamic states and our entangled states, those were static objects. And the resource theory formalism can be extended to the study of channels as well, right? So in the channel picture or the dynamic object picture, your states are channels. And then your operations are processes that map one channel to another. Okay, so we're going to a higher level. Yeah, and as a comment, actually, all of Shannon information theory can be seen as a dynamic resource. Why is that the case? Well, because what you're doing is you want to try to simulate a noiseless channel, right? And that's your, in any communication setting, that's your resource that you're trying, that is of greatest value to you, a noiseless communication channel. But in principle, you have noisy channels. So you're trying to simulate this maximal resource, which is the noiseless channel. Okay, right. So in this dynamic resource theory, our states are channels, and our free operations are transforming one state to another. And so these type of operations are sometimes known as supermaps or quantum combs. And let's see how this works. So I start off with one dynamical object, a channel. And what I can do is I can introduce a pre-processing map. So this is now some pre-processing channel. I can introduce a post-processing channel. And then I can connect the two, the pre and the post, with some side quantum memory. And then what I get at the end of the day, if I kind of abstract this, is I get a new channel going from T to T bar. Right? So I started off with an object S to S bar, and then I added these additional components, and I get something that's going T to T bar. Okay, and that's what is known as a supermap. Okay, any supermap can be implemented in this way. Okay, so I want to look at a specific example of channel transformations, and it's related to this notion of compatibility. All right, so first let's think about the general process of making a quantum measurement. All right, abstractly, what are we doing? We have some device that has a quantum input. This is the state we're measuring. It has a classical input, which is a set of instructions telling our device what to do. And then it has our measurement outcome, which is a classical output here. Okay, so you can think of this as a QC to C channel, right? A quantum input, classical input, and then a classical output. And so we could ask, well, what sort of resources could be present in such a device? Well, one resource that is certainly present is quantum memory. And the reason could be that, imagine, so since we have two inputs, it might be the case that in fact, our quantum state arrives before our measurement instructions arrive, right? And if you think about from an experimental perspective, you're the experimenter, you may change your mind on what particular measurement you want to perform, right? So there's some freedom here that we're allowing on the measurement instructions. And so what we'll want is we want some quantum memory that can store our quantum input until the moment that we make our mind what it is we actually want to measure. All right, so that would be some resource that could be present in this measurement device. And it's tied back to the ability to freely choose what instructions we want to imprint onto our measurement device. Okay, and so what I want to show you is this idea of quantum memory is actually equivalent to a resource of measurement incompatibility. So take a step back and just introduce the idea of measurement incompatibility. So historically, incompatibility has been understood in terms of this notion of joint measurability under sequential measurements. And so imagine this scenario. Actually, this is like if you open up Sakurai and you read his introduction when he talks about Stern-Gerlach experiment. For me, that was the first time I really was exposed to this idea. It's a great introduction. So if you haven't read it, I highly recommend it. But it looks something like this. You imagine you prepare a quantum state rho and you perform some measurement, observable A, you get an outcome, little a. And then you, at some later time on that same system, you perform another observable B. Okay? So here, what you're getting out are two classical outputs, little a, little b, corresponding to the measurement outcomes. And you do this many times and you look at what happens, you get some statistics that are described by a probability distribution. Call it P1 AB. Okay, probability distributions over both those outcomes. But now we switch the order of the measurements. Now we do observable B first, followed by A, right? And we do this many times, we acquire statistics, and it'll be described by a different probability distribution, P2. So it turns out that in quantum mechanics, these distributions, P1 and P2, are not always the same, right? Which means that the order of your measurement matters. And so we say that A and B are incompatible if the joint distributions are different for some input state rho. Okay. Another way of phrasing this is that the joint probability distribution is not well defined because it depends on the order of measuring. Okay, yeah, Stern-Gerlach experiment. You can imagine first measuring in the Z direction, then measuring in the X, or you can measure X first and then Z. And here you see you get two different probability predictions. If I go for ZX up would be 1/2, ZX up would be 1/4. And because I'm starting off here with say an eigenstate of the sigma Z operator. Okay. So what's known, very easy to prove, that observables A and B are incompatible if and only if they don't commute. So let's think about this. Let's actually think about the converse. Let's think about when they do commute. Why does this allow for joint measurability? Well, the reason is because we can, if it commutes, we can simultaneously diagonalize these guys, right? Meaning that I can find a common set of eigenprojectors. And then what I can do is I can do some fine-grained measurement. So I'm taking my eigenprojectors PA and PB and I'm resolving them into an eigenbasis EK. So I can first perform this mother or this fine-grained observable C, and then I can do some classical post-processing. Okay. So in other words, I can construct a device that does the following. I input row, I measure C, I get outcome K, and then depending on whether I want to measure A or B, and then I just feed my classical data to either of these classical channels. And so everything on the right here, this is all classical post-processing. And then it allows me to define a joint distribution AB in terms of this classical post-processing here. Okay, so now I want to make this link to quantum memory. All right, so the idea is that we can implement compatible measurements without needing quantum memory. And so the way it goes is as follows. Remember that an abstract measurement device has a quantum input, a classical input, and then a classical output. So here's my quantum input. It comes in, I measure it right away. This is my C observable. Then I feed the K to some classical post-processing map here. And then my measurement instructions, they can arrive whenever they want. I don't need it to arrive before the quantum memory or before the quantum state. And I don't need any quantum memory to store my state row. I measure it right away. And then what I do, actually where the memory is coming in, is I have classical memory, because I have classical memory to store this outcome K until the particular measurement instructions X arrives, right? So it maps the demand for quantum memory into a demand for classical memory. Right. Okay. Yeah, crucially, the classical instructions can be delivered asynchronously with the quantum system. And you could imagine that this doesn't need to be the case. In fact, incompatible measurements don't allow for such an implementation. If you have a family of incompatible measurements, what's happening is that the measurement instructions have to be fed into this internal measurement device. Okay, so in fact, if X is going to come after the arrival of rho, then you need to store rho before you actually make this measurement, this POVM here. All right, yeah. Okay, so here's the comparison between the compatible measurements on the left and the incompatible measurements on the right. And you see that what happens is that on the right, you need quantum memory because you have to feed the quantum state and the instructions in at the same time to the POVM, whereas on the left, you don't need quantum memory. Okay, so I'll go through this somewhat quickly in the interest of time. So suppose you're in the laboratory and you build some classically controlled measurement device. Okay, I don't care what's going on inside the box. It's just some black box that does this property. And a very natural question is, what is the full operational power I can do with this box without having to introduce any additional quantum memory? Right. So I'm thinking of this quantum memory actually as a resource. So I'm framing this very natural question that arises in anyone's laboratory, and I'm phrasing it now into a resource theory question, where I've identified quantum memory as the expensive resource. Okay, and so this being a resource theory question, now we can use some of the tools of a quantum resource theory. So we can use these ideas of quantum combs and supermaps. So what are the free operations we're allowed to do? So starting from this device, we can do some classical preprocessing. We can do some quantum preprocessing. And we can also take our classical input and we can store it in classical memory. Okay, so we're not allowed to use quantum memory. That's a resource for us. That's not allowed. But we can store our classical input in some classical memory. And then we can do some post-processing as well. All right. And again, combining all this, what we get is some new measurement device as a quantum input, classical input, and a classical output. And this defines for us a resource theory of measurement incompatibility, where the free channels are compatible families of measurement. And here we have our free operations, which it looks somewhat complicated, but actually they make intuitive sense because it's basically everything you can do without quantum memory. Okay. And so then let's say the following. Let's kind of go full circle here. So I want to say if I have some measurement device, if I can convert it to another measurement device using these operations that we just outlined, we'll say that n is majorized by m, right? To use this terminology we saw in the beginning, and we can interpret this as saying that n is more compatible than m. Okay, and go back to our statistical decision problem. We saw that when we were comparing channels, we said that M was majorized by M if and only if for all payoff functions, N had a higher maximum value than M. And so what you can show here, and this is a result that we obtained recently, is that actually the same thing can be concluded here. That now I have this measurement device, and I can convert my N to an M. I can convert to another measurement device if and only if for all payoff functions, my maximum score of N is no less than the maximum score of M. Okay, again, and this is highlighting just the common features. You have these two very different looking problems. One is with what you can do measuring quantum systems, and the other is some statistical process that you might encounter at, I don't know, a casino. But it turns out that they have this unified structure to it. All right, so I have one slide of conclusions and some future problems to think about. So my main sales pitch here is that a quantum resource theory offers a well-structured approach to studying different features of quantum mechanics. And I earnestly believe that this sort of philosophy can help in practical ways in developing quantum technologies. And specifically what it inspires is this feedback between experimentalists and theorists. So you could imagine that the experimentalist would say to the theorist, here's what I can do experimentally, right? Now I want you to come up with all the ways, given my limitations, all the different quantum information tasks I can perform. So the theorist could go and do that. And the theorist could say, okay, here's what we can do. But if you could go one step further, if you could give me one more free operation, right, then we could do something even more amazing. We could do some process that was not possible before. So I think it allows for this nice feedback. And I know everything's not clear-cut theorist versus experimentalist, but this is just the rough idea of the type of interaction you can have between the math theory of a subject and the experimental implementation. Okay, another idea is that this approach could be extended to study computational complexity. And you think about what does computational complexity theory do is it basically classifies problems under different restrictions, right? Can I solve this problem using a polynomial time algorithm? That's a restriction on what you can do. And so I think this would be an interesting thing to pursue, is actually tightening this, making a resource theory here in terms of these computational complexity classes. And going beyond quantum, you can use resource theories to study post-quantum theories or classical theories as well. I mean, there's no reason why this resource theory approach can't apply there, and it can tell us something about quantum mechanics just by understanding the limitations and the possibilities of classical theories and post-quantum theories. Okay, so that wraps it up for me.